Right. Yeah, it's important that I work at Honeycomb.io, which is an observability company, by the way, because this talk comes out of our company value. Everything is an experiment. And it's like it's on our website, on the about page of our company. It's very official at Honeycomb that everything is an experiment. Um, and the part that I like on here is that it emphasizes it's what we learn that matters. But here's the thing. I don't think that everybody at Honeycomb has the same idea of what an experiment is. I mean, look at this cute little logo. It's adorable, but why is the liquid going up in a curve? I guess that emphasizes that we should look for surprise, which is true. But the thing is, we don't have the same idea of an experiment because an experiment doesn't mean the same thing at every level of a system. So today I'm going to talk about experiments in 4 different viewpoints and ways of doing them at different levels of the system. And the important part about all of them is that in the end, everything is an experiment if we look at the results. If we get that learning, then okay, whatever we did was an experiment. I like this value and it makes me smile because I majored in physics in college and I really liked physics lab where we did little experiments like, okay, we're going to put a ball on a ramp, it's going to roll down, and we're going to time how long it takes until bam, it hits the block at the bottom. And then we're going to compare that to, and then we're going to write all our numbers down. We're going to keep track of all our results. We did this by hand then. And then we're going to compare them to a theory. This says A equals G sine theta provided by teacher. And from that theory, we can calculate how long it should have taken for that ball to roll down the ramp, and then we can compare that to the number we measured. And this teacher is very happy that we got a fairly consistent 55% error rate on that. So it's an experiment because we have a characterization, and a characterization could also be a theory, it could be a mental model, but Wikipedia uses the word characterization, and I like that. A picture of how we think the world works. And from that, we can have an expectation about this particular test, what outcome should it have, and then we can look at the results. Now, in physics, we don't actually look at the results and use them to update our model. We're like, oh, our experiment was 55% wrong. But we don't change A equals G sine theta. We continue to think that. So more of a toy than an experiment. But this technique of systematic testing and measurement has served me really well in software. Starting out as a programmer, it served me really well in debugging, and it continues to serve me really well in exploratory testing and learning new systems. So it's really good. I like the technique of stating your expectation. Whenever I try something, I say, pairing is really good for this, I say out loud, okay, this time we're going to get this error, or this time we're going to get a new error, or when I click this, I expect this to change. The epitome of stating your expectations is unit tests. Don't look at these, they're just unit tests. And in them, you write explicitly expect result to be this thing. And then you run them and it fails because you just wrote this. But you expected that. You expected that to fail. And then you get to change the test or change the code. I love this. We get to like update physics in the little world we're doing experiments in until that test passes. And then sometimes the test continues to not pass or it fails in the wrong way. And I have to spend a bunch of time updating my characterization of how the code works, and maybe I insert some brand new scientific instruments that I just added to the world in the form of a console.log in this case, or maybe I use the debugger. The debugger makes every experiment at this level easier. But I do the investigations and I update how I think the world works until I'm right and the test passes again. So I have a characterization of how I think the code works. It gets updated in debugging. When I look at the results, and I am going to learn over and over and over, apparently, to read the error message. Read it, read the whole thing, read the middle of the stack trace, actually look at the error message. And then there's like CI, because if we put our unit tests in CI and then it fails the build to force us to look at the results, all to keep our vision of the physics of our little software world consistent with reality. Another piece of this is that in a controlled systematic experiment, we need to control the environment, or at least describe the environment in which this fact is true. So in the physics experiment, we drew the little diagram of the experimental setup. And in programming, we do this in the Docker file, what operating system and what else is included to make this thing actually work. And then we have the Docker Compose or the Kubernetes YAML or whatever on top of that. And we have learned over the last few decades to do our best to make our infrastructure reproducible or at least describable so we can say what is required to make our stuff work. So that's describing the environment. But at some point, these systematic tests and measurements work really well on our computer, and they work in CI, because again, controlled environment. But at some point, we have to put them in production, and that's a whole different game. Now we're in a distributed system. There's network involved. There's other services involved. Maybe some of them are LLM components, and they're non-deterministic. Somewhere in this picture, there's going to be users, and we know they're non-deterministic. That's the point. So we have to be able to handle a lot of things. A console.log does not cut it anymore. Log search doesn't cut it. We need log analysis. We need to do things at the level of many things are happening. Some of them are random, and some of them I really care about. So we're on to measuring and adjusting. Do the deploy, and then see whether it had the effect we wanted, see whether people are using it, see whether they're giving it the input we expected, or our categories are actually completely not the ones that users are actually following. It's a different kind of testing. So here's an example from Honeycomb a few weeks ago. My colleague, Martin Holman, was doing something in the session database, and he happened to notice this graph of the free space on the session DB is going down, and it's going down rather fast. I think this is over like a month, and it's going down by about 5 gigs, and it's just over 10 gigs. So in 2 months, we're going to run out of space and crash, and no more sessions for us. So that's bad. First, he like tried deleting a bunch of sessions, and that databases didn't actually change the free space, and had to fix the trigger that should have notified us. But then he's like, okay, now how can I actually fix this? Where are these sessions coming from? So he does a query over all of our events that are happening in our system, and he's like, who's messing with the sessions database? And there's a lot of selects, and there's some inserts. Okay, we care about those inserts. Why are those inserts happening? So narrow it down to just those, and then graph a count. And there's like 20,000 sessions at a granularity of 1 hour. 20,000 sessions an hour is a lot. We might have 2,000 concurrent users in our product. And also, usage of Honeycomb is really spiky. It's high during the day, and it's low at night and on weekends, and this is not spiky. What is up with all these sessions? So he clicks on one, and he gets into a distributed trace. We're an observability company. We have distributed tracing. And they're like, no user in session. And this doesn't match his characterization of expecting sessions to be about users that are logged in. These are not logged in users. Why do we even have these? And the answer is in the second span, push redirect URL. Aha! When somebody tries to go into Honeycomb at like a deep link and they hit the login page, we need to save the page they were trying to hit, that redirect URL, so that when they log in, we can send them there. That would be useful, except where are we trying to send them? Slash. That's like the default. That's the homepage. That's boring. Why are we saving anything for that? How many of these 20,000 sessions an hour are going to slash? And we can count that. And it turns out that in whatever time period, 6 million of them are going to slash and like 40,000 are going somewhere else. Okay, well, what if we just didn't save those? Maybe that would be useful. So you can see what happened when he did that deploy. Sessions created just plummets because now every robot that hits our login page is not triggering an insert into the session DB. So and he can go back and check the redirect URLs and find that indeed we don't have slash anymore. They're all interesting. Some customer is hitting us repeatedly at some deep URL and that nice even line, but it's only 50 an hour, it's fine. And then the satisfying one, the free storage space. Whoop! Now we have way more storage space, and more importantly, that rate of storage space decrease is very low, and we are not going to run out of space in this database in the scope of time that we care about right now. So that was great. This teaches us to look at the results of our deploys and everything else, especially look for surprise. The surprises are even more interesting than the results we were looking for. So that's a useful kind of experiment in this system. But there's one more thing. I want to point out that Martin started from an observation. We often start from an observation of something that is not as we would prefer it, or not as we expected it. In his case, it was the free space is dropping faster than we expect, and it's too low. But if we notice why we're doing an experiment at all, what is it about the system that seems wrong to us that we're trying to change, that makes it a little bit more of an explicit experiment. Okay, and then we get to the level that involves users in the system. And at this point, we give up on having a controlled environment. This is definitely an open system, and we are working within it. And in an open system where you can't predict what all is going on, what we can do is check for effects of our interventions. This, just like in biology or medicine, medicine is the canonical field here, where they do randomized controlled trials, and that's the new gold standard when the scientific method doesn't apply to an uncontrolled system. A randomized controlled trial like this one, 15 years ago when I was done having kids, I asked my doctor about birth control methods, and he's like, oh, there's this new one that the studies show 0 unplanned pregnancies and also no effects, because they're checking for, does this cause cancer? Do people have heart attacks? All the other surprises that they're looking for. So that's what we do in medicine. And we can totally do that in our distributed systems, this kind of randomized controlled experiment. So here's one. Liz Fong-Jones ran this one a few years ago. Amazon put out a new chip architecture that you could run lambdas on. Now, we've run AWS lambdas pathologically almost. We run so many because they're in our database. When someone makes a query that covers a lot of data, we spin up a bunch of compute in Lambda, like 10,000 at a time, to serve that query so that all of our queries can be fast enough. And it's a lot, and it's unpredictable. So we're very interested when they say it's faster and cheaper than the existing lambdas. So Liz set up an experiment, and we're going to run. We're hoping that we can run half on the old architecture and half on the new architecture and see those cost savings. So here's some results from the first run of this. The orange line is the new chip, the ARM chip, and the purple line is the old chip, and the top one is the slowest, P99 requests. So these are the slowest lambdas, and you see the orange line is mostly above the purple line. We could zoom in on the numbers. And sure enough, the P99, the slowest ones, is like twice as long for the new chip. And then the median is also longer. So on average, they're also taking longer, which negates any cost savings. So they cost at least as much, and they're slower in the worst case. Meh. So Liz rolled it back. This is Liz in Slack changing the feature flag. Feature flags are amazing for this. They make this whole class easier. And she has rolled it back, so we're only running 1% on the ARM chip, make sure we don't break it, and 99% on the old chip. And this is another property of a great experiment, is if you're willing to back it out. Because when we say everything is an experiment, one of the things we mean is we're going to keep learning from what we do, and that means we're always willing to change what we do, because even if we've been doing it the same way for 3 years, everything is an experiment. We can change it. Right, Liz backed this one out, and then she went in and investigated why are they so much slower. Some of it turned out to be capacity constraints. AWS didn't have as many of the new chips, so they couldn't spin up 10,000 in 10 seconds. Well, okay, 10 milliseconds. And then we were on Go 118 at the time, which was the current version, and it was missing some optimizations for the new chip. And then our compression library was also like running in the old command set and having to be emulated. It wasn't ready. So Liz went back and fixed each of these. Well, I mean, okay, AWS increased their capacity. We upgraded to Go 119 before it was GA. And Liz put in a PR to the compression library. And now, this was like yesterday or the day before that I took this graph. We're running 1% the old chip and 99% the new chip. So the colors are switched. The old chip is now orange, and the ARM chip is now purple. So the count at the top shows we're running all the purple ones. And the P95, the duration, is about the same. And if I zoom in, here's the important bit. The average cost of the new one is 20% lower for the whole execution. So when 20% of our Lambda bill is a lot. So this one illustrates that sometimes the rest of the system just isn't yet compatible with the new thing you're trying. This is a tricky bit because sometimes stuff that didn't work before, it might work now because the rest of the system has adjusted. Jerry Weinberg has a thing, everything new is broken, because the rest of the system isn't ready for it. I like to add, and everything old is stupid, because I don't know why it's there. So this compatibility thing is a tricky bit of our experiments, and it makes them a lot slower. So this is why we do migrations. And our deployments get a lot slower and more gradual because we need every new version of the system to be compatible with the one before. We need our new version of the data to contain all the information the old version did, and we need the system to be compatible with both versions for a little while. With feature flags, we'll put the feature flag in, and then with a deploy, and then we'll do the release and flip the feature flag in production, and make sure that, check the results of that, and then we'll go back and remove the code. So there's multiple steps because we're keeping it compatible with the wider system at each point. This is why a few weeks ago, Google had at their login screen, there was a banner, watch out, we're going to change the way the login screen works, for weeks. And then like a week ago, they actually changed the way the login screen worked, and there was a banner, watch out, we've changed the way the login screen works, until I dismissed it. When what you're about to do isn't in line with user expectations, then you've got to adjust user expectations and then make the change and make it all gradual to keep it compatible at every step. And that's how experiments are successful, because if you just shove it into a system that isn't compatible, it doesn't work. Okay, so here's one that involves actual users. That one was really just between us and AWS. At Honeycomb, the green team was in charge of growth, of like new user experience. And they did a project called Navbar Reorder. The model of growth at Honeycomb, of people value from Honeycomb, is somebody makes an account, and then they have to send us data, and then something happens, and they get value in the form of clues, information from their observability. And our characterization is that those question marks, they need to run a query. If they run a query, they're going to see the power of Honeycomb. That's what we're amazing at. But by observation, they looked at where new users go after they get data into Honeycomb. And one of the things they clicked on the most, they looked in Amplitude, which has like graphs, like where people go, these interesting spaghetti things. And they learned that people go here. They get to this settings page, default granularity, completely useless. No, you don't want to be here. This is for like much later. And they get here because it's number 3 on the nav bar, right under new query, is data sets, which sounds like tables, which is accurate, but it doesn't actually give you the data in your table. It gives you just settings. So they were like, what if we change the name to data settings and we move it down to the bottom? And then we change new query to query because that's less scary somehow. And we move a bunch of the more useful stuff up. And we're like, maybe their expectation was fewer people will click on data settings, more people will run a query. And then for the environment, we're going to use brand new users to Honeycomb, only on free teams, because none of the account execs whine about what we do with free teams. And we're going to give half of them the new nav bar and half of them the old nav bar. And so they did that for a month, and then they got data. And sure enough, way fewer teams clicked on data settings at the bottom than clicked on data sets at the top. And more people clicked on good things like SLOs and boards and query. And did they run more queries? Well, yes, but it's not statistically significant. So there's a better than 1 in 20 chance that this variation was random. So we can't really say, but they didn't run fewer queries. So that's good. They looked at the results, and this has an interesting effect of compatibility of this change. My researcher at Honeycomb, Justin, he admits that a lot of this UX research, often you're taking something obvious. If you move it down and you name it more accurately, will fewer people click on it? Duh. But it's a lot more convincing if you have numbers that say that indeed fewer people click on it and more people do good things and maybe more of them run queries even. There's a lot of other teams at Honeycomb that are each responsible for one of those navbar items, and nobody wants their navbar item moved down. But they could argue with the green team, but they won't argue with the numbers. So sometimes the results aren't really for you. Sometimes they're for the decision makers, and it's a matter of compatibility with the wider sociotechnical system. So this is the interesting part to me. The sociotechnical system that is us as developers and our company and the running code in production and the tools that let us see what's going on in there. This is where I'm interested in making change the most. And this part of, or this level of the system is a semathesy. So a semathesy is a learning system made of learning parts. Emphasis on the learning. So our teams are a semathesy because we as humans are always learning. And we learn from each other, and collectively we learn together. We create knowledge and what did Sin call it? Experiential alignment of moving forward together. And the code is part of the semathesy, the running software in production. It learns from us because we change it. And we learn from it because it throws exceptions. It tells us what the user's doing. If we have great observability, we get more of that. That it helps the flows of learning, which is why I work at Honeycomb. So our team is a semathesy, a system based on learning. And that means that experiments are great because we learn from them, right? But here's the thing. Randomized controlled trials are not great for this. Read this beautiful paper a couple weeks ago by Megan Stevenson, and she's a PhD in statistical methods and generally the kind of research that she's criticizing here. And she points out that over 50 years of randomized controlled trials in criminal justice, that's her error, what we can learn from looking at them as a whole is that actually randomized controlled trials don't teach us anything. Maybe this is not the source of knowledge that we need. We learn that the limited scope interventions that lend themselves to these tests show us that social change is hard to engineer. And by engineer, she means like linear causality, push this button, expect this to happen. Because stabilizing forces push people back toward where they were, and a success in one setting does not port well to another. Your agile pilot team may be super agile and very happy, but it's operating in a sea of waterfall for years. Even within the same company, you can't just copy something that worked in one place and put it in another because every semathesy is different. The more we learn together, the more different from other sematheses we get. And that's constructive in that we're doing different things. We need different knowledge and we need to be together, but it really makes the same interventions not transfer. We can't control the environment of these. We can't do randomized controlled trials here. We can describe the environment, and that can help. But Stevenson cites the iron law of evaluation, the expected value of any net impact assessment over a long period of time and over attempts to implement it widely, the expected value is 0. And this is 20 years old. She didn't come up with this today. This is just accepted. And yet people continue to play the academic publishing game because other forces in the system push them back to continue doing the same thing. But we don't have to. We don't have to. Randomized controlled trials aren't perfect. As an update, this is a study from 2018 on that Escher device that looked at things that had happened since the 2011 study, which lasted a whole 2 years max. And it's like, oh, actually, there were some unplanned pregnancies and a death and some nickel allergies. And they took it off the market. Now, I'm lucky. I'm fine. I didn't have any of these complications. But it just points out that keep looking at the results. Don't stop at the end of the quarter when you met your KR. Don't stop at the end of your 2-week sprint that you were trying the thing. Keep looking at the results. And that's where we can learn even more. Because in these sociotechnical systems, there are ways to work in this. If we let go of the gold standard of the numerical scientific methods and numerical statistical methods with the controlled trials, there are ways that we know to work in these systems. And domain-driven design is one of them. Domain-driven design gives us explicit recipes for working in both the social and code parts of our system. Because we can create language that improves the flow of learning between all of them. And we create boundaries around that language, and there's explicit techniques for crossing those boundaries and focusing on that. And I love that. Domain-driven design is totally a sociotechnical technique. And now that we're in the sociotechnical system, what does work is action research. And this is capitalized because it's like a real thing. It's been a thing since the 50s, and it's grown in popularity. I learned about it from Brené Brown. Brené Brown is a researcher into wholeheartedness, and vulnerability, and how we as people get meaning from life. And she's got a chapter in the appendix of one of her books, at least one. I think I got it from this one. About her research methods. And her research methods are action research. Action research says, this is an open system. I am not going to study it from outside. I'm going to get down in there, and I'm going to talk to people, and I'm going to figure out maybe how things work and how to make it better. Action research is not about studying from a distance and then ignoring the results. It is about getting in and making change consciously and also learning and doing a little bit of science that we can share. An important part is that the results are not just numbers. Brené Brown is interviewing people and then carefully categorizing the responses and counting how many different responses point in this direction and then going in this direction. It's also more of a flow than a time-boxed activity, because you don't need to start with the characterization. In fact, she says, put the literature review at the end, right before publication. Start like Eric started, without looking at someone else's implementation of the categories. He remarked this morning that he was glad he didn't do that because he learned more from starting from scratch and implementing it himself. So you don't need to know what you're doing already. Have a character, or evolve a characterization as you listen to people, as you notice what's happening in the system. And some of that can be numeric. I don't know, maybe you're counting pull request comments or something, but most of it is talking to people and noticing what they say, noticing whether they're chatty and Slack or quiet, and then asking them why. And we keep making observations. Another clear technique for experimenting in social systems, or sociotechnical systems, our teams in particular, is Agile. I believe that the most important Agile ceremony, the only important one, is the retrospective. You don't even have to do it formally, but if you are looking at the results of whatever the heck you're doing and tweaking it a little bit and then looking at the results of that, then you can get anywhere you need to be. Now, it will not be the same place some other team needs to be, but it will be where you need to be. So retrospectives are great. As an example of trying something in a team, my partner Avdi is working with a team right now, and he noticed that there was one person on the team, let's call him Nate. He's the purple developer, and he wrote this system. He wrote the system over the last 10 years. He knows it inside and out. He has all the knowledge of what's going on. And there's a couple other developers on the team, they're blue and green here, who are trying to help, but they're not getting anywhere. And Avdi observes that the knowledge in this team is concentrated in Nate. Nobody else has a clue of what's going on. And so he thinks maybe we'll try ensemble programming. And ensemble programming, it's also called mob programming, but ensemble is a nicer name. It's where the whole team works together, everyone's looking at one screen, one person is typing, but the thing is, the person typing is not allowed to make decisions. Every decision about what to type, what to implement, has to be voiced by the rest of the team, and then the person typing, the driver, can put it in. And then you take turns typing. So he was like, let's just try this. And they tried it. And the surprise was they loved it. Wow. Everyone felt included. They kind of knew what's going on and why they were doing it. And so this team did ensemble programming daily for weeks, months. Eventually, they got the knowledge spread around, and they'd gotten most of the benefit. And also, they were super tired of how long it took to switch. And that's a compatibility problem with the development environment, but whatever. They did an ensemble daily forever, but it was still a successful experiment and did spread some knowledge around. Okay, I can use that example to go through, this is my blueprint for a rigorous experiment within the team. These are the things that I want to ask myself beforehand if I'm going to be serious about this. First of all, what's the observation that is triggering this experiment? What is not as you would prefer it? In Avdi's case, it was the blue and green couldn't get anything done. Characterization, what do you think is going on? In his case, it was that all the knowledge is stuck in purple developer. And then if you make your characterization explicit, you can often test it in smaller ways than a change the team kind of experiment. For instance, if this is what's going on, Avdi can ask blue and green, how's this particular project going? How are you feeling about it? And they can be like, we would expect them to be like, well, I think I need to make the change here, but I'm not sure. I'm worried about what's going to happen over here. I don't know what else will be impacted. They're going to express low confidence. And then he can ask Nate the same thing, and he's like, well, you just blah, 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 blah. Because the word just and obviously are a clue. I like to replace them with, I can't explain it, but. Because this is a clue that the knowledge of this software system is embedded so deeply in Nate's brain that he cannot imagine someone else not having that knowledge. So he could test it that way, and yeah, he does get answers like that. And so then he comes up with an action. What do we think we can do about it? This case was ensemble programming. And then there's the question of why. Why does he think that action will work? And this is back to the part of the characterization too. Now it could be, well, it worked for some other people. I heard about it at this conference and it sounded cool. And really, if you're going to invest 2 hours and you're perfectly willing to back it out, and that's like the worst that can happen, go for it. But in this case, Avdi did have some real theory about why this would work, because ensemble programming is designed to spread knowledge in the team. That's why the driver isn't allowed to make decisions. Every decision is voiced. Everyone has an opportunity to ask questions. Everyone takes a turn at the keyboard, so you kind of even out who knows all the different tricks. And the tricks and the fastness get passed around, and it levels both the knowledge of the software and of how to do things. And people develop more shared language because they're using their mouth words instead of just typing in the code. So he has reasons that he thinks that'll work. And then what results are you looking for? State your expectations. And often this is not numbers, it's just how might you notice that it's working? It doesn't have to be counting. So if this is working, he would expect blue and green to gain more confidence in the code. He might notice that it's not working if one person is talking all the time. That's not helpful. And then what else might you keep an eye on? He should keep an eye on the WIP and the throughput for the team, and also in his one-on-ones, the well-being of each individual. So if you list this out and then come back to it later when you're looking at the results to remind yourself of what you were going to check for, I call that a pretty rigorous experiment. But realistically, this is what I actually ask. What's the worst that can happen? So most experiments that I do are somewhere in between. This is like the minimum. And if it's not too bad, I can try it and not worry about, like, I don't know, making a worksheet of what I expect to see. This is fine. In all of this, when we try stuff in our symathesis, the worst that can happen is that we learn something. Now, this is action research, emphasis on the action. So learning something is not the only goal. But learning something is an important effect of what we're doing, because this is how our symathesis gets stronger. I like to think that everything that we do has two outputs. It's whatever effect we were trying to have on the outer world and the next version of ourselves, the next version of our team. So the learning really matters. Earlier today, Sin had this slide. The gold is in the struggle. It really is about the journey and who we become. And that's why this flow of experimentation, of action research, worst that can happen is we get to be better people with a better understanding of the world and each other. Because if we're really looking at the results, it will change us. We will be different. Our teams will be different from who they were before and from each other. Which means that when you ask the usual question that you get from managers of if it works, now how do we scale it up? Yeah, I've never seen Agile scale well, because Agile teams work beautifully because they're not hierarchy. And as soon as the hierarchy tries to make them bigger, what do you get? You get more hierarchy, and that's not the thing. Experiments, the randomized controlled trials show that if something is small enough to be a small experiment, it doesn't scale up in breadth and in time. Our small experiments aren't going to make the wide-reaching, long-term change we'd like to see in our sociotechnical system. The increase in quality that we'd love to have, quality of life and quality of software. Sooner or later, we run into the iron law of the breadth of over a very large integral, the value goes to zero. The only thing I've ever seen that really has promise for a bigger change in the bigger system is this talk by Beth Andersbeck from Agile 2022. And it wasn't recorded, but Beth made a video, and it's at this link. And Z is talking about a radical culture of culture building. Radical because it's not the same as the system we have. It's not incompatible with our methods of organizing things. But the URL, I'll give a QR code at the end. But yes, this is important. I can't summarize the whole talk here, but it's about, instead of standards, let's have a fabric of norms. Because norms give us the consistency that we need, while also the flexibility for doing the appropriate thing in each piece, in each team, in each piece of the system. And it's about structures different from the ones we have, but structures that can reproduce themselves, not by copying, but more like a biological reproduction, by spreading and creating knowledge as it's needed. And I love this talk, so I'm glad you were taking pictures of it. This is really important. That link, by the way, goes to Gumroad, which asks you to pay for the video. Give Beth money, please. She deserves it. And her work is important. So at all levels of our company, and our software and our users and our programs. We have different ways of thinking about experiments, and we need to use the one that's appropriate to the level that we're working at. And the other thing about Beth's technique is this is not fast, and this is not easy, but it is where you want to be if you're going for the long game of really making meaningful change. In the meantime, let's keep learning at all levels. Let's do all the things sometimes, but in the end, I'm happy if you just look at the results. Read the error message, ask people how they're doing, form relationships in your organization so that you can ask questions and get real answers, because that's the fastest way to make these experiments useful. And if you look at the results and really listen to people, then you will be changed. And that's a good thing. Also from Sin's talk today, the change we are seeking will inevitably change us. When you're working in a system with other people, you need to bring the other people into the change. You need to listen to them. You need to incorporate their ideas, even if their ideas are not as good as yours. If you bring them in, if you sacrifice the purity of your vision to the collectiveness of building consensus and moving forward together, then you have compatibility, and then you might actually succeed. And one more thing, if we do this, if we don't keep these experiments to ourselves, but we share with each other what we tried, why we thought it would work, what situation we were trying it in, and what happened, then we can compare with each other. And it's not going to be like, it's not like physics where we all really do live in the same world. We live in different social worlds, all of us. But there's commonalities, and we can look for patterns and heuristics as a community. If we do this, then we're doing science. Because science is not something you can do as an individual. It's something we do as a culture and a society. And if we share this with each other, blog it, talk on podcasts, share at conferences like this, and I mean the hallway track, not just the stage, then we can create knowledge together, and we can grow as a community. Because we don't know how to do software yet. We are still figuring this thing out, how to do this really well. And we can do it better together. And if we find the heuristics that help us, and we share those principles, and we continue to create common language, like by agreeing with each other at this conference, then I can be better at my work of being a semathicist, of participating consciously in the semathecy in a way that moves it in a direction in which all of us can thrive, and we can thrive within our environment. That's what I'm looking for. And that is what I have for you today, except I also have stickers.